I ended the last video asking you whether you thought f of x equals x squared and g of x equals square root of x are inverses. The answer is no, not quite. Let's take a look at why not. Remember that inverses undo each other. So if f of x equals x squared and g of x equals square root of x were inverses of each other, then f of g of x and g of f of x would both have to equal x. F of g of x, which is f of the square root of x, which is the square root of x squared, certainly does equal x, so that works just fine. But g of f of x equals g of x squared equals the square root of x squared is tricky. You may be tempted to think that the square root and the exponent cancel, but there's a problem. The square root function, which is more accurately called the principal square root function, never outputs negative numbers. But couldn't x be negative? To make this more concrete, let's suppose x equals -1. Then g of f of -1 would be the square root of -1 squared, which would be the square root of 1, which is +1. We did not get back to the x we started with. The square root of x squared is not equal to x. To be super precise, the square root of x squared is equal to the absolute value of x. Because x squared and square root of x don't perfectly cancel each other out in both directions, they aren't true inverses. Another way to understand why they cannot be inverses is to look at their graphs. The graph of f of x equals x squared is a parabola opening up with its vertex at the origin. And the graph of g of x equals the square root of x is just the top half of a sideways parabola opening to the right. As we've discussed before, f of x equals x squared is not one-to-one. It fails the horizontal line test because we can find outputs that come from multiple inputs. This is exactly what was happening when we tried to compose the functions. F of -1 and f of 1 both equal 1 for f of x equals x squared. So it isn't one-to-one, so it cannot have an inverse. We can visualize the issue in another way by reflecting the graph of f of x equals x squared across the line y equals x. This results in the graph of a full sideways parabola opening to the right. But a parabola opening to the right fails the vertical line test. It's not a function. This is exactly why we force the square root function to only output non-negative numbers, limiting ourselves to just the top half of the parabola. So the bad news is that no, x squared and square root of x aren't true inverses. But the good news is that if we restrict the domain of x squared, we can create a function whose inverse is square root of x. We just have to limit ourselves to the right half of the parabola, which is the half that creates the square root function when we reflect across the line y equals x. So the inverse of the square root of x is x squared, where x is greater than or equal to 0. This is useful because it allows us to find inverses for all sorts of quadratic functions and functions involving square roots. We just have to make sure to restrict the domain of the quadratic function so that we are only using half of the parabola. Example, let f of x equal 2 times the quantity x minus 1 squared plus 4. Find a domain on which f of x is 1-to-1 and find the inverse of the restricted function. Once you've done enough of these, you can probably start to see the restricted domain without having to draw a graph. But I don't want to pass up an opportunity to practice graphing a transformation of a function. F of x is a transformation of x squared. Specifically, it has been stretched vertically by a factor of 2, shifted 1 unit to the right, and shifted 4 units up. This puts the vertex at 1, 4, and since the graph would normally go over 1, up 1 from the vertex, now we go over 1, up 2. To make this graph 1-to-1, we need to get rid of 1/2 of the parabola. While it's possible to use either half, it's a little more straightforward to use the right half. and we can talk about why in a minute. If we restrict to just the right half, the restricted domain is 1 to infinity. Can you see how we could have figured that out without drawing the graph? All that matters is the x-coordinate of the vertex. And we can find that just by looking at what number is being added or subtracted from x inside the parentheses in the formula or function. Once we have our restricted domain, finding the inverse of the restricted function is just like finding the inverse of any one-to-one function from its formula. We start with y equals 2 times x minus 1 squared plus 4. Then we switch x and y, and we solve for y. To solve an equation like this, the most efficient way is to start from the outside and work our way in. So we're first going to deal with this plus 4, the furthest thing away from y, which we're trying to isolate. So we subtract 4 from both sides, then divide both sides by 2, and now we have x minus 4 over 2 equals y minus 1 squared. Now here's the only subtle part, and where it matters which half of the parabola we chose. In order to get rid of the exponent of 2, we need to take the square root of both sides. Normally, if we are solving an equation and we put the square root in, we also have to write plus or minus because there could be two solutions, one positive and one negative. But we've restricted our domain to take just the right half of the parabola, which means our inverse will be only the top half of the sideways parabola. The top half is going to come from the positive square root, not the negative. So we can just say that y minus 1 is the square root of x minus 4 over 2. If we had chosen to use the left half of the original parabola, then our restricted domain would have been negative infinity to 1, and we would have used the negative root and said that y minus 1 was equal to negative square root of x minus 4 over 2 instead. To finish solving, we just have to add 1 to both sides to get that y is the square root of x minus 4 over 2 plus 1. This is the inverse of f of x equals 2 times x minus 1 squared plus 4, restricted to 1 to infinity. For our final example, let's let f of x be the square root of 2x plus 2. Find a formula for f inverse and what is the domain of f inverse. For this example, we don't have to restrict the domain of f of x because square root functions are already one-to-one. So we can jump right into finding the formula for the inverse. Starting with y equals the square root of 2x plus 2, going to switch x and y and solve for y. First, we need to square both sides. We don't have to do anything special here because like we saw at the very beginning of the video, squaring a square root does just cancel it out. It's only taking the square root of a square that we have to worry about. So x squared equals 2y plus 2. Now just subtract 2 and divide by 2 to get that x squared minus 2 over 2 equals y. We can split that up into two fractions and say that y equals x squared over 2 minus 2 over 2. So the inverse function is 1/2 x squared minus 1. To find the domain of the inverse function, we have to think about the original function. On its own, the domain of 1/2 x squared minus 1 would be all real numbers, but then it wouldn't be one-to-one. Remember that the domain of the inverse function is the range of the original function. f of x equals the square root of 2x plus 2 has range 0 to infinity since it is a square root function that hasn't been reflected or shifted vertically. So the domain of f inverse is also 0 to infinity. You could also look at 1/2 x squared minus 1 and see that it hasn't been shifted horizontally. So the x-coordinate of the vertex is still 0. So taking the right half of the parabola, since f of x equals the positive square root of 2x plus 2, emphasis on the positive, would be 0 to infinity.